All right, we good. So everybody got this stuff back, right? Grades have been posted on OSIS if y'all want to check it out. Don't take it to heart, right? It's your email. Not the one with the numbers, the other one. The one without the numbers. Yeah. That's like your Brightspace login and all that and Cutie first. No, it's a different one. For the email, for the like BC email, that one. Yeah. I really don't know my own. Really? Yeah. All right. For real? Oh, all right. Just know that like don't take it to heart, right? Because remember the whole policy. I'm dropping the lowest test grade, right? You guys can do corrections. There, like the homework, y'all got time to catch up with it. So if you look at it and you see like a bad grade, just don't think that like, oh, that's the whole grade. Yeah. It's just like a formality, something we got to do. Yeah. Well, I got you. Yeah. I mean, y'all got good grades. I ain't got to worry. So, let me ask you guys. Anybody got any questions though? No questions. Everybody's good. Homework is good. For everybody. I apologize about tonight's homework. I know it's only like 2 questions. I'm so sorry. Yeah. Yeah, see, I wish it was more. I know. I'm sorry. I know y'all really deserve like 10, 20 questions, but like nah, it's not that complicated. Nah, it's not. When you see today's lesson, it's not complicated. My lesson is more complicated than what it is. Like when you see what it is, it's just calculated work. Mhm. All right, so if nobody got any questions, let's just jump into for today, all right? The grades, everybody got A's in my heart. All right, so this is what we're doing today, right? We're gonna do standard units and area under the standard normal distribution. This is mad easy. Don't worry. But I am gonna drag it out. I'm gonna drag it out. All right. So what we're doing is we're gonna talk about z-scores and raw scores. All right. Z-scores and raw scores. So normal distributions vary from one another in 2 ways. The mean mu, maybe, I don't know if I'm blocking. The mean mu, sorry, all right. The mean mu may be located anywhere on the x-axis, and the bell shape may be more or less spread according to the size of the standard deviation sigma, right? The differences among the normal distributions cause difficulties when we try to compute the area under the curve in a specified interval of x values, and hence the probability that a measurement will fall into that interval, right? So I'm trying to find the area under the curve, aka the probability of something happening, right? A continuous distribution. It's fun stuff, fun stuff. So it would be futile, right? It would be a futile task to try to set up a table of areas under the normal curve for each different mu and sigma combination. We need a way to standardize the distribution so that we can use one table of areas for all normal distributions. We achieve this standardization, by considering how many standard deviations a measurement lies from the mean. In this way, we can compare a value in one normal distribution with a value in another different normal distribution. So the next situation shows how this is done. So I'm about to show you how, I'm about to give y'all the sauce real quick. And don't worry, it's mad simple. It's mad simple. Give y'all a little example real quick. So suppose Tina and Jack are in two different sections of the same course. Each section is quite large, and the scores on the midterm exams for each section follows a normal distribution. In Tina's section, the average mean was 64, and her score was and her score was 74. In Jack's section, the mean was 72, and his score was 82. Both Tina and Jack, right, were pleased with, that their scores were each 10 points above the average for each respective section. However, the fact that each was 10 points above the average does not really tell us how each did with respect to the other students in the section. All right. So in this figure, we're going to see a normal distribution of grades in each section. All right. So it's not about how well you do, it's how well you do compared to your classmates. All right. Ooh. So Tina's 74 was higher than most of the other scores in her section, while Jack's 82 is only an upper middle score in his section. Tina's score is far better with respect to her class than Jack's score is with respect to his class. All right. So think of it like you know like how we have different sections of like Math 23 and stuff. So you would have some people's sections might be harder than other people's sections, right? So it's how well did you do in that section as compared to someone else in another section, you know? Your 40 over here might be like 100 next door kind of thing, you know? Something like that. So just to kind of visually talk about what we're seeing, right? In this story, this would be Jack's class and Tina's class right here. Let's pull that up a little bit more there, right? So you see how Jack's section, it's a normal distribution still, but it's more spread out, right? Go ahead.
So, okay, let me try to guess.
Yeah.
So that means since the average, the curve is a lot shorter, I'm guessing that the grades were more evenly distributed.
Yes.
Than Tina's.
Yeah, you could say that, right? So like there was a whole plethora of grades here. There was A, B, C, D, E, F, all I, N, G, right? All of that was there, right? But in Tina's section, most people got a C, right? And she just got better than, oh, sorry, a D. Whoops. And she just got a little bit better at a C, right? So that's what makes her grade more stronger than Jack's grade. Even though Jack got a higher grade, right? It was so evenly distributed, like the standard deviation of this is so large compared to here, right? That it's less or more meaningful, right? So yeah, when you hear people from other classes like, oh yeah, I got a 2 on my exam, their class might have been harder than your class, you know? And I've seen that in tutoring also, believe it or not. Right? Oops, sorry about that. So the preceding situation demonstrates that it is not sufficient to know the difference between a measurement X value and the mean of a distribution. We need also to consider the spread of the curve or the standard deviation. What we really want to know is the number of standard deviations between a measurement and the mean. That is, this distance takes both the mean mu and the population standard deviation sigma into account. All right. So we building it up. We building it up. All right. So we can use a simple formula to compute the number Z of standard deviations, a measurement X, and the mean mu of the normal distribution with standard deviation sigma. So the number of standard deviations between the measurement and the mean, right? This is going to be our Z, right? And what it's telling us is the difference between the measurement and the mean divided by the standard deviation. All right? That's it in words. In symbols, this is the way it looks on your formula sheet. All right? So this is in chapter 7 on your formula sheet. The z-value or z-score, also known as a standard score, gives the number of standard deviations between the original measurement x and the mean mu of the x distribution. So the formula is z is equal to x minus mu over sigma. All right? All on your formula sheet. And this is the formula you use for your homework as well. All right? That's it. Again, I apologize for the homework. Yeah, we're getting to that. Yeah, I got you. Yeah, we got lots of examples today. So the mean is a special value of a distribution. Let's see what happens when we convert x equals to mu to a z value. So if we said that our x is the mean, right? That would mean that we want the mean minus the mean, which is just 0, right? So when the z value is 0, we're going to see what happens. All right. So the mean of the original distribution is always 0 in standard units. Remember that, right? So when I'm talking about a z value, the mean is going to be 0. Remember that. This makes sense because the mean is 0 standard deviations from itself, right? And x value in the original distribution that is above the mean mu has a corresponding z value that is positive. Again, this makes sense because a measurement that is above the mean would be a positive number of standard deviations from the mean. Likewise, an x value below the mean has a negative z value. All right? And that's all corresponding to the formula x minus mu, right? If x is bigger, it's going to have a positive z value. If x is smaller than the mean, it's going to have a negative z value. That's all I'm saying. All right. So we building it up. We're building it up. Go ahead. So part of your homework is I'm going to give you a x, I'll give you a mean, I'm going to give you a standard deviation. I'm going to ask you to give me the z value back. You plug it in, click enter, and you type it in. That's half your homework. All right. And I'm sorry, it's only 2 questions.
Can you print the first line, please, again?
This one?
No,
This one?
yeah, no.
All right, so come back to this. So the mean of the original distribution is always 0, right? In standard units. So whenever I'm talking about a z value, right? Like a plain z value, the mean is going to be 0, right? And that's going to be in the center of the graph. I'm going to show you that in a second. All right. I just want y'all to get that known. This idea is going to come back when we start talking about the calculator. All right. I'm going to show you guys some more calculator tricks today. All right. So x values and corresponding z values, right? So an x value in the original distribution, when x is equal to mu, right? The z value is 0. If x is bigger than the population mean, then the z value is going to be greater than 0, positive, right? X is like some random number I'm gonna give you, right? I'm gonna give you a story. The story is gonna have a mean, and the story is gonna have a standard deviation, right? But to compute the probability of whatever the story is asking, right? We have to convert it to a normal distribution, a z value, right? So this is just telling you when the z should be positive and when the z should be negative. If the x value is bigger than the mean, then the z value is positive. If the x value is smaller than the mean, then the x value, and then the z value, excuse me, will be negative. And then that's it. Simple, simple, simple stuff. All right. Before we go into an example real quick, just to recap, what does a standard score tell us? All right. So a standard score or z-score of a measurement tells us the number of standard deviations the measurement is from the mean. A standard score close to 0 tells us the measurement is near the mean of the distribution. A positive standard score tells us the measurement is above the mean, and a negative standard score tells us that the measurement is below the mean. That's it. All right. That's what a z tells us. If it's okay, let's look at an example real quick. Right. It's gonna be good too, right? But we're gonna be talking about pizza. So a pizza parlor franchise specifies that the average mean amount of cheese on a large pie should be 8 ounces, and the standard deviation only 0.5 ounces. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it is made with 6.9 ounces of cheese, right? And mad cheap. Assume that the amount of cheese on a pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. How many standard deviations from the mean is 6.9, and is the pizza parlor in danger of losing its franchise? All right. I'll tell y'all a story about this afterwards. But I'm sure y'all could probably guess which franchise I'm talking about. A pizza franchise, pizza franchise.
Domino's.
Fuck them. All right, since we want to know the number of standard deviations from the mean, we want to convert 6.9 to the standard z units, right? So we're trying to find the z value, right? We're trying to find how many standard deviations from the mean it is. So we're taking the sample pizzas, which was 6.9.
That's X.
That's X, right? I'm gonna subtract that from the mean, which we know is 8, right? And divide that by the standard deviation, which is 0.5. Calculator, boom, boom, boom. I get negative 2.2 standard deviations, right? So without going further, we know that negative 2.2 is less than 3, right? Standard deviations away from the mean, right? So what the heck does that tell us? Let's talk about it. Let's talk about it real quick. So the amount of cheese on the selected pizza is only 2.2 standard deviations below the mean. The fact that z is negative indicates that the amount of cheese is 2.2 standard deviations below the mean. The parlor will not lose its franchise based on this sample, right? Because 2.2 is below the mean, is less than 3, that's why. Simple, right? So we have seen how to convert from X measurements to standard units Z, right? We can easily reverse the process to find the original raw score X if we know the mean and the standard deviation of the original X distribution, right? So simply solve the Z-score formula for X, right? And that's how you find the raw score formula. Raw score formula is on your formula sheet. All right.
X,
Mm-hmm.
sigma.
That's it. All right. So here you go, raw score formula. Given an X distribution with mean mu and standard deviation sigma, the raw score X corresponding to the Z score is X equals Z times sigma plus mu, right? Again, all on your formula sheet. So you would use this situation if you were given a probability itself and ask, how does that probability translate into the story? Right? So we're asking like a reverse question. Well,
Like, if they ask, well, what's the raw score, we would just take those numbers and nothing.
well, you're gonna take the probability that they give you, the percentage. You're gonna find the Z value for it, and then you just plug in all the other numbers here, and then that's it. Yeah. It's not bad. I got you. I got you. Let's talk about some more examples real quick. All right, so Rod figures that it takes an average mean of 17 minutes with a standard deviation of 3 minutes to drive from home, park the car, and walk to an early morning class. One day it took Rod 21 minutes to get to class. How many standard deviations from the average is that? Is the Z value positive or negative, and explain why it should be either positive or negative? So the number of standard deviations from the mean is given by the formula, right? Z is equal to X minus mu over sigma, right? Where we have 21 minutes that one day that he did it. On average, he does 17, right? So it's 21 minus 17 divided by 3. That's given us 1.33, right? So the Z value is positive. So we should expect a positive Z value since 21 minutes is more than the mean of 17 minutes, right? Fair enough. All right. Let's answer this question. What commuting time corresponds to a standard deviation of Z is equal to negative 2.5, right? An interpretation, could Rod count on making it to class in this amount of time or less? So we take our raw score, X is equal to Z times sigma divided by mu, plug in our value. We have Z, negative 2.5. We have our standard deviation of 3. We have our mean of 17. With a calculator, and we get 9.5 minutes. So no commute times at or less than 2.5 standard deviations below the mean are rare. All right. So reasonably, he can make it to class, right?
Wait,
You always given the Z, or you have to find.
You're always given the X and the mu. It depends on the question. Some questions, they give you the X, they give you the mu, they give you the standard deviation. Other questions, they'll give you the mu, the standard deviation, they'll give you a probability, and you have to figure out Z. You know, or X. Let me see. We're getting to that. Yeah. We're building up to it. We're building up to it.
I was going to have the data 2.5, but
They gave it to us in this situation. Yeah. Some questions they're gonna give it to you. Some questions you have to find it for yourself. But we haven't talked about how to. We're getting to that. All right. So the basic structure of the formula for the standard score of a distribution is very general, right? When we verbalize the formula, we see that Z is equal to the measurement minus the mean of the distribution divided by the standard deviation of the distribution, right? So we will see this general formula used again and again, in particular when we look at sampling distributions, right? And when we use the normal approximation to the binomial distribution, we'll get into that next week, right? And we will see this formula. We'll also see it when we discuss the sampling distributions for proportions, right? Which you guys will see in the 4-year school. Yay, right? And for confidence intervals and for hypothesis testing, which you guys will see here as well. Way in November, but coming. All right. So that's what we're building up to, right? Our inferential statistics. All right, so standard normal distribution. All right, now we're getting to the probability. If the original distribution of X values is normal, then the corresponding Z values have a normal distribution as well. The Z distribution has a mean of 0 and a standard deviation of 1. The normal curve with these properties has a special name, excuse me. I'm about to talk about it. It's about to get good right here. So the standard normal distribution is a normal distribution with mean mu is equal to 0 and standard deviation sigma is equal to 1. All right. Really important. Remember that. Mu is equal to 0, standard deviation is equal to 1 when we're talking about a standard normal distribution with a Z. All right. So any normal distribution of X values can be converted to the standard normal distribution by converting all X values to their corresponding Z values. The resulting standard distribution will always have mean is equal to 0, mu is equal to 0, and standard deviation sigma is equal to 1. All right, remember that. All right, that is hilarious. Yeah.
Your pencil.
Yeah.
Oh,
Yeah. That's
I
funny.
forgot mine, so.
That's really funny. I mean, I said it was important and you got the right instrument, right? All right, so let's go back to this, all right? Little review of what we were doing last week. So the standard normal distribution, right? Our mean mu is in the center right here, right? And that's 0. And the standard deviation here is 1, right? So that's why from 0, we go to 1, to 2, to 3, and back. -1, -2, -3, or -1, -2, -3. All right. So this is a little review of our empirical rule that we did last week, right? I know that homework wasn't so bad.
Oh, I need to go over it first.
Empirical rule.
So after class, we can look at that. So let's talk about something, right? What does the standard normal distribution tell us? When we have the standard normal distribution, we know the mean is 0, the standard deviation is 1, and any normal distribution can be converted to a standard normal distribution by converting all the measurements to standard Z scores, right? That's all we know. All right. Let's get to the real idea here, right? We want to talk about the area under the standard normal curve. This is going to be dope. So we have seen how to convert any normal distribution to the standard normal distribution. We can change any X value to a Z value and back again. But what is the advantage of all this work? The advantage is that there are extensive tables that show the area under the normal curve, right? For almost any interval along the X-axis. The areas are important because each area is equal to the probability that the measurement of an item selected at random falls in this interval. Thus, the standard normal distribution can be a tremendously helpful tool. All right. All right, so let's keep it going. So now we're going to talk about the standard normal distribution table that you guys have. This is, I think, table 8. If you guys look in the formula sheet, not the last table, but the one right in front of it, that's the normal distribution table, and that's what we're about to talk about right now. All right. So using a standard normal distribution table, Using a table to find areas and probabilities associated with the standard normal distribution is a fairly straightforward activity. However, it is important to first observe the range of z values for which areas are given. This range is usually depicted in a picture that accompanies the table, right? In this text, we will use the left tail style table. This style table gives cumulative areas to the left of a specified z. Determining other areas under the curve utilizes the fact that the area under the entire curve, is 1, right? Taking advantage of the symmetry of the normal distribution is also very useful, right? The procedures you learn for using the left tail style normal distribution table applies directly to the cumulative normal distribution areas found on your calculators, right? So we can use this lesson to translate it into finding the normal distribution on your calculator. Right, so that's what we're going to get into, AKA the second half of your homework. All right. So let's start off with an example, right? So we want to use table 3 of the appendix to find the describing area under the standard normal curve, right? So here's our question. Find the area under the standard normal curve to the left of z is equal to -1, right? So what we want to do first, right? Let's draw our distribution, right? My artwork is not so good, so we're going to draw our distribution and we're going to find that area, right? So here's our distribution, right? Z is equal to -1 is here, and I want this area to the left of it. That's what I'm looking for, right? That blue area to the left, all right? So first shade in the area to be found on the standard normal distribution. So you shade in the blue part, as shown in the figure. Notice that the Z value we're using is negative, right? This means that we will look at the portion of table 3 in the appendix, right, for which the Z values are negative. So on your normal distribution table, you have a negative side and you have a positive side, right? Because my Z value here is negative, I'm going to look at the negative side, all right? In the upper left corner of the table, right, you will see the letter Z, right? And the column under Z gives us unit values and tenths values for Z. The other column headings indicate the hundredth value of Z. So table entries give areas under the standard normal curve to the left of the listed Z value. To find the area to the left of Z is equal to -1, for example, we will use the row headed by -1.0 and then move to the column headed by the hundredths position 0.00. This entry is shaded in the table, and we'll see that the area is actually 0.1587. All right, so let me show you guys the table real quick. So this is your table, right? Table 7.2, right? You guys all have this, by the way. And again, this is not the last table, the one right in front of it, right? I'm looking at the negative Z values here. I'm going to come down to where -1 is, right? And then this is -1.00. So I'm going to come up to the top right here, where the 100 place is, and where do they intersect that? Where they intersect that, that is your probability, right? So 0.1587. Right? So you come across here, that's your -1.0. And for the second O over here, you're gonna look at the top. And where do they intersect that? That's your probability. That's what I'm looking for. Okay? Similar, yes. So I'm gonna ask you, what is the probability of Z less than -1.0? So like this.
And then we'll have to
Right, z less than negative 1.00. And then you find the probability and you tell me, oh, the answer is 0.1587. And that's it. In web work, you just click submit after that. And that's the whole thing. It's similar and related. Similar and related. All right, let's flip the script a little bit, right? Let's say that I want to find the area to the left of z equals positive 1.18, right? So now we're talking about a positive z value, all right? What's the first thing I want to do? Let me look at the distribution. All right, so here's how it will look. All right. Our z value is 1.18, right? So we grab our line right here for 1.18, shade everything to the left, right? So 1.18 is right here. And then I want what's to the left of it, so I want less than, so I'm going to shade everything to the left. And then that's it, right? Knowing that information now, you can take it and go straight to the chart. Go ahead, you can look it up and tell me. Okay. 118, right? So you're gonna go to where 1 is, then go to where 8 is. Where do they intersect that? All right. So we're gonna go over it. Don't worry, I got you. No, it's 0.8810. That's what it is. Yeah. And the positive 1.18. So in this case, we are looking for an area to the left of a positive z value. So we look in the portion of the table 3 that shows the positive z value. Again, right? We first sketch the area to be found on a standard normal curve as shown in the figure, right? Look in the row headed by 1.1 and move to the column headed by 0.08. Right, where they intersect that. Desired area is shaded, right? And the area to the left of it of 1.18 is going to be 0.8810. All right, let's take a look at that. So if I'm looking at the table, right? Here goes the table right here. So I go down to where the row 1.1 is, right? So here goes the row 1.1. Right? Just to recap, right? I'm looking for probability of z less than 1.18, right? So I go to the row of 1.1. At the top of the page now, I go to the 0.08, right? That's how I get the 18, right? So 1.1 and then the 8 at top, right? And I look at where do they intersect that? Where do they intersect that? And then that's my probability right there, right? 0.8810. Huh?
So you basically take the last digit and that's it.
Right, the last digit is the top. The first 2 is the row,
Yeah.
right?
So, wait, they're gonna ask you, find it at 1.18, right?
Right, you find me the probability of z less than 1.18, and then you would look this up like that. Let's talk some more. All right. So the area of a standard normal distribution is located in the appendix as well as in the end papers of the text. So spend a little time studying the table and then answer these questions. So as z values increase, do the area of, to the left of z increases? Yes, it does, right? So as z values increase, we move to the right of the normal curve, right? And the area will increase, all right? So basically I'm saying this is a normal curve here, right? If z was here, as it's moving to the right, this area is getting bigger, right? So that's what they're saying. It should be a larger number as we keep increasing the z value. All right. Talk about a flip question. If a z value is negative, right? So now we're on the other side of the curve, right? Is the area to the left of a z value less than 0.5? Yes, it is. Remember that a negative z value is on the left side of the standard normal distribution. The entire left half of normal distribution has area 0.5. So any area left of z equals 0 will be less than 0.5. All right. So just to illustrate what they're saying, I have a normal distribution like this, right? And this is z equals 0 right here. This is cutting the graph in half, right? So if the middle part is cutting it in half, anything that will appear below it is going to be less than half, right? Less than 0.5. That's what they're trying to say. Mhm. And then when it is at 0, that is half, right? That's 0.5 when it's at 0, like on top of 0, right? Let's ask a flip question real quick. So if a z value is positive, is area to the left of z greater than 0.5? Yes, it is, right? So positive z values are on the right side of the standard normal distribution, right? And any area to the left of a positive z value indicates the entire left half of the normal distribution. Interesting stuff, right? So keep mentioning the word left, right? But what happens if the distribution is not to the left? Let's say it was to the right or something. Mm-hmm. Not, it would always be positive, but it would just be flipped, right? So let's talk about that real quick. About to flip this. Why? It's good. This is so simple. Wait till you see your homework. That's where you're going to be disappointed. So let's talk about how to use a left tail style standard normal distribution table. So for areas to the left of a specified z value, we use table entries directly, right? So if I ask you what's the probability of z less than whatever answer you get off the chart, done. That's it, right? For areas to the right of a specified z value, right? You're going to look up the entry on the chart, and whatever answer you get, you're going to subtract it from 1. So 1 minus point whatever, right? Another way you could do this is if I ask you what's the probability of z greater than whatever, right? Even though I'm giving you, like, let's say a positive number, you could flip the script, go on the other side of the chart and look up that same number and then copy down that number, right? And the reason why that works is because the graph itself is symmetrical, right? What's on the left is the same thing on the right, right? So, and then if you have an area that's in between two z values, right, where one is bigger than the other, right, you subtract the z1 value, which would be the bigger value, from the little value, and that's it. So you look up both z values on the chart. One of them is going to be bigger than the other, right? You subtract the bigger one from the little one. That's it, right? And that's whenever I ask you, what's the probability in between this situation and that situation, right? If it's okay, just want to show you guys some graphs just to illustrate what I'm saying. So let's take this graph, for example, right? The area to the left of this giving z value, right? I'm asking you, what's the probability of z less than some number? You're going to copy it straight off the table. We're done. That's the end of the conversation, right? That's when it's less than. All right. Now let's say that it's greater than, right? So now my question is, what's the probability of Z greater than some number, right? So boom, here goes the Z value, and I want to know what's this area to the right of it, right? The way you do it is you take the whole distribution, which we know is equal to 1, and you subtract it from the area to the left of it. Whatever the Z value is that I gave you. If I said what's the probability of Z greater than 1.2, I'm just making something up, right? 1.2, right? You're gonna find the area that's less than 1.2, and you're gonna subtract it from 1. That's it.
Why you not just want to sound?
I got you. We're building up. We're building up. Yeah. So you go down to where on the row, right? Look for row 1.2, right? And then it's 1.20. So you look at where the 0 is, where they intersect that. Right? And then that's the number. Yeah. Right. So if I was asking you what's the probability Z greater than that, you're gonna do 1 minus 0.8819, whatever, in the calculator, and give me that answer. And that's it. Yeah. All right. Now, let's say you don't want to do the 1 minus. There is another way as well. Right? So let me show you guys that real quick. The 1 minus, it makes more sense. Right? An alternative approach is to use the symmetry of the normal distribution, right? So say I want the area to the right of the Z value. So I want Z greater than 1.20, for example, right? Another way to do it is because it's symmetrical, right? Positive Z is the same as negative Z. You can actually look up negative 1.20, and that's a straight answer if you want to do it that way, without doing the 1 minus whatever. Okay. Me personally, I love the 1 minus thing. It just makes sense to me. So that's another way to do it. And last but not least, I could ask you, what is the probability of Z or in between two Z's, right? So I have a Z1 and a Z2, right? And I want to know what's that area in between, right? So not add them, subtract them, right? So you take the area from the big Z, which is all of that, and you subtract it from the area of the little Z, and that's how you get the area in between. And that's it.
Yeah, that's how finding the difference. Yeah.
Exactly. Just finding the difference right here. All right, so you just hit the minus sign in the calculator and boom, that's it.
But you would give us the Z value, when we have to find the Z value.
Depends. Yeah. It depends on the story. So figure this thing, right? Illustrates the procedure using the table 3 values, right? The areas of the standard normal distribution to find any specified area under the standard normal distribution. Again, it is useful to sketch the area in question before you use the table, right? So I highly recommend you guys learn how to sketch the area that they're asking about, all right? This will help you with using the calculator tremendously. All right. So notice that the Z values shown in the table, right, of the appendix are formatted to the 100th position, right? It is convenient to round or format your Z values, bless you, to the 100th position before using the table. The areas are all given to 4 decimal places after the decimal. So give your answers to 4 decimal places after the decimal. What this is saying is, right, we have that formula, X minus mu over sigma, right? When you do all the math on that, you might get a long number, right? 1 point, right? Round it off to the nearest 100th. And then you can use the table, because the table goes up to the 100th place, right? That's all it's saying. You'll see that in your homework. No. All right, make another little comment. The smallest z value shown in the table is negative 3.49, while the largest value is 3.49. These values are respectively far to the left and far to the right on a standard normal distribution, with very little area between either value. So we will follow the common convention of treating any area to the left of z with a value smaller than negative 3.49 as 0. And similarly, we'll consider, right, any area to the right of z, right, when z is equal to 3.49 as 0, right? We understand that there is some area in these extreme tails. However, these areas are less than 0.0002, right? So let's get real. Some very specialized. Get that next line for you. Oops. Applications beyond the scope of what we're doing here do need to measure areas of corresponding probabilities in these extreme tails, but in most practical applications, we follow the convention of treating the areas in the extreme tails as 0. All right. So sometimes you might put it in the calculator, for example, and get like some crazy small number, which is correct, right? It is the correct answer, right? But you can just simply say 0 if it's like really extreme, right? All right, so convention for using the table of the appendix, treat any area to the left of the z value smaller than negative 3.49 as 0. Treat any area to the left of the z value greater than 3.49 as 1. All right. And that's that. Let's try an example real quick. About to try an example real quick. Let's say that I ask you guys to find an area between 1.0 and 2.70. All right. I'm asking y'all to find me that area real quick. What am I going to do first? All right. Draw the distribution. All right. That's first. All right. So when I draw the distribution, this is what I get.
So what's equals to make
The graph,
graph
basically.
like that?
Yeah. All you need to know is that 1 is bigger than 0 and 2 is bigger than 1. And that's basically it, right? And you want the area in between there. That's all we're asking. Huh? You can shade it in, yeah. It doesn't have to be crazy. It could be as simple as like you just doing this. I can read that and understand, you know?
So they're gonna be worded.
So it's gonna be worded as what is the area or the probability, right, from z equals 1 to z equals 2.70, and that's it. So look up the answers first and then subtract the two answers from one another. Yeah.
So you would have answered like this.
In the table, yeah. The both of the z's, you're gonna look up those two answers and you're gonna subtract them, and then that's it. So you look up 1.0
And then 2.0.
and 2.70, right? And then you're gonna subtract them from one another, and that's it. Easy peasy.
But 0.00, no.
Like 1.00. Yeah. So you go to 1.0 and you go to the 0 up top, and where do they intersect that? Right? Whatever that decimal number is, you write that down and say on a piece of paper. And then you find the 2.0. So you're gonna go, excuse me, the 2.70, right? So you go to the row where 2.7 is and the 0, and wherever they intersect that, that's the second number. And you subtract the big number from the smallest, and that's it. All right? Mm-hmm. So when you look it up, right, this is what you should get, right? After we sketch the diagram, the area between 1.0 and 2.70 is the area to the left of the 2.70, so all of that, right, which is 0.9965 when you look it up, minus the area to the left of 1.0, so this part here. Right? And then-
answer
Is whatever that difference is,
Okay.
right? So we have 0.9965 minus 0.8413, and we get 0.1552.
Yeah.
That's it. Sure. Plug it out and.
Yeah, you can plug it in. Thank you.
Is the wrong one?
It was wrong one.
I'm sorry.
Wait.
Sorry about that. All right.
And then you have to round up.
No, just give me the answer. That's it. All right, let's look at another example real quick. This is gonna be a flip question. Huh? If it's negative, just use the other table. Yeah, same, but the same idea.
Okay.
But here's a flip question though, right? Find the area to the right of 0.94. Right to the right of it. So here's how we gonna do that. There is, go to 0.9 and then 4. Right, so the first thing we do, we're gonna draw a distribution, right? We know that 0.94 is bigger than 0, so we know it should be on the right side of 0, right? And then we want the area to the right of it, we want greater than, so you're just gonna shade to the right of it, right? For this area right here. Right? That's what we're looking for. But remember that our table only gives us areas to the left, right? So to find the area to the right, right, we have to do 1 minus that area. Right?
It would be 1 minus 0.8264.
Mm-hmm. 8264, very good. So first we sketch the graph, and after that, to find the area to the right of 0.94, right? We use the entire area, which is 1, right? And we're gonna subtract that from the area to the left of the 0.94, which is 0.8264. So in your calculator, 1 minus 0.8264, boom, you get 0.1736. Done. You got it?
Yeah.
Can't find it? Got you. So look. Let me take a look, see if I show you.
Thanks for the entire numbers were one. All right, so we are now forced to go. We're gonna look at this now. 0.94.
Maybe next week, guys. Next week. I got you. Okay. So that's it. You found it? All right.
Yeah, on my computer. Yeah.
All right, so far this whole class was for like a couple of people in here, mostly you, right? Because I know you ain't got the right calculator, right? So that was the whole thing. You don't? What you got? Oh yeah, so it's for you too. For everybody else, let's talk about the calculator. You know how to do the integral? The integral, like mentally? That's impressive.
By just looking at it.
Oh yeah. Yeah. Yeah,
I wanna be able to put numbers.
I just type it in still.
Yeah, it's like-
Yeah. All right, so let's look at another example real quick. But now I'm gonna hook y'all up. I'm gonna hook y'all up, right? So let's look at this example right here. So here's the question, right? They want to know what is the probability of Z greater than 1.15, right? And this refers to the probability that the Z value lies to the right of 1.15 and shade the corresponding area under the normal curve, right? So step one, we draw our distribution like we have here, right? We find where the 1.15 is. We know that it's right there, and we want the area to the right of it, right? So here's your blessing. You can do this in the calculator, right? So here's how to do it in the calculator. So let me make this a little bit smaller. All right, I think we're good, right? So once again, I want the probability of Z greater than 1.15, right? Just for fun, let me see what the answer is, right? So our answer here is 0.1251. That's the answer. But we're going to talk about how to do this in the calculator, right? So to do it in the calculator, the first thing that you need to do is draw the distribution, right? Draw the distribution. So here goes my distribution. I know that 0 is in the center, and what they're looking for is 1.15, right? So I'm going to come over to where 1.15 is, right? And I want the area to the right of it, right? So I want this area over here. That's what I'm looking for. All that area over there. You can just use scratch marks, right? I just have the benefit of having a highlighter, right? Anyway, let's say that we're gonna do this in the calculator, right? What you're gonna do is you're going to press, oh wait, hold on, let me get I think my red pen will pop on this a little bit more. Let's do that, right? So we're gonna go to second. Oh, y'all really can't see that. All right, that's the blue button on the calculator, second. Then you're gonna go to where it says distribution. Distribution is where the data button is, right? I know you can't see it here, but you can see it on the recording. So that's why I'm still writing on it and showing it that way, right? And then when you get there, right, you're gonna press across. So we're going to the right, to where DISTR is. DISTR stands for distribution. And then I want you to go down. So you're just gonna hit the down button to where it says normal CDF.
Number 2.
Normal CD. Is it number 2?
Yeah.
Okay. I don't have it memorized, so I need help. All right, thank you. So when you hit normal CDF, what comes up?
It says mean.
All right, so they're looking for our mean, right? Remember, this is a standard normal distribution. So what's my mean?
1 point.
No, what's my mean? 0, right? And then this is a standard normal distribution, right? So what's my standard deviation? 1. 1. Very good, right? And then what comes up after that? Sigma's 1, right? And what comes up after that? Lower limit and upper limit, right? All right, so let's talk about that. Next on your calculator comes up lower limit and upper limit. If I'm not mistaken, there's something written there too, right? -1 E99. and 1E99. All right, don't type nothing yet. Let me explain what those are real quick, right? So -1E99 is actually an idea from calculus. It means negative infinity, right? 1E99, right, means infinity, right? In computer science, we know this as machine zero, right? But for your benefits, for what we're gonna do, that's gonna mean infinity, right? So that's talking about like the entire graph, right? That's what that means. Anyway, for our question, remember we drew our distribution. I got you. I'm gonna get there right real quick. So for our distribution, we drew it over here, right? So our lower limits is gonna be the 1.15 right here, right? That's what you're gonna put for lower limit. Your upper limit, remember, all of this is being shaded, right? So your upper limit is infinity, which is gonna be the 1E99. Just leave it the way it is, right? So all you're doing is changing the lower limit to 1.15. Then you press enter, and it should give you the answer.
So the value is 0.125.
Perfect. And that's our answer.
If you wanna go on the calculator.
If you want to do it on the calculator. All right. So mind you, right, when you're doing these questions, right, there's no way to prove to me that you're using the table or the calculator. So do whichever one is easiest for you. I think the calculator is the easiest. All right. That does negate the whole lesson of today, but this lesson was for 2 people in the class. You're welcome.
So I don't got all the extra work for that.
There's nothing to show. I ask you this, give me the answer. That's it. All right. If you wanted to show a little bit of work, you could do the 1 minus this, right, for less than, and then find the probability of less than and just do the subtraction. That would show a little bit of work, right? But that's it, right? If I asked you a reverse question, what is the probability for it less than, right? What are you gonna do? You're gonna change your upper limit, right? And then you leave the lower limit as -1E99, and then boom, give me the answer. If I ask you a question, what is the probability of Z in between 2 numbers? You change both of them. The small number is the lower limit, the upper number is the bigger, the bigger number is the upper limit, right? Click enter, give me the answer. That's right.
They on the test will give us the mean and the mean.
Yes, yes,
So I
yeah,
just plug it into the
right.
calculator.
But for a standard normal distribution, what's the mean?
The mean is 0.
Right, and what's the standard deviation? Good. All right, so just remember that. So that's that. All right. So this is the situation when we have a normal curve, right? What happens when I don't have a normal curve? Right? So say I give you an X value instead, and you have to convert that to Z and all that. Let's talk about that. All right? More specifically, I'm talking about how to find the area under any curve. All right? So the area under any normal curve. Let's take a look at this. So normal distribution areas. In many applied situations, the original normal curve is not the standard normal curve. Generally, there will not be a table of areas available for the original normal curve. This does not mean that we cannot find a probability that a measurement X will fall into an interval between A and B. We must do, what we must do is convert the original measurement of X, right, from A and B into Z values, right? God bless you. So this is what we're talking about here. So procedure, how to work with normal distributions, all right? So to find the area and probabilities for a random variable x that follows a normal distribution with mean mu and standard deviation sigma, convert the x values to z values using the formula, right? And then use the table to find the corresponding areas or your calculator, your choice. Right? Make sure you draw the distribution. Matter of fact, to answer your question in the back, right? Drawing the distribution, that could be considered work. Right? So I'll give you credit for that. You know, just drawing out the curve. Let's look at an example real quick. Ooh, this is a hard example too. Dang. All right, let's go through it. Let's go through it. So normal distribution probability. Let X have a normal distribution with mu is equal to 10 and standard deviation sigma is equal to 2. Find the probability that an X value selected at random from this distribution is between 11 and 14, right? So symbolically, this is how it looks, right? Find the probability that 11 is less than or equal to X, which is less than or equal to 14, all right? You can,
Use the
but
graph for that.
you should graph it still first,
I
right?
mean, this, would you use the table for that?
You can. Mhm. I'm gonna talk about how to do it using the table, but you can just type it in the calculator and have a good day. All right? So real quick, this is the distribution that we're talking about here. Right? So our mean is 10, which is in the center, right? And our standard deviation is 2. So one standard deviation to the right, boom, 2, 3, 4, etc. To the right and to the left. We want to know specifically, right? What is the area or the probability between 11 and 14? So you draw the distribution, you shade it, right? Shade that area between 11 and 14, right? And then you convert it to a z, right? So since probability is corresponding to the area under the distribution curve, right? Since probability is corresponding to areas under the distribution curve, we want to find the area under the x curve above the interval from x equals 11 to x equals 14. To do so, we will convert the x values to standard z values and then use the table of the appendix to find the corresponding area under the standard normal curve, all right? So that's the sauce right there. So here's what we want to do. Right? So we use the formula. Z is equal to x minus mu over sigma. Again, you guys have that on the formula sheet, right? I want to convert the 11 and the 14, right? Why? What happened?
My brain is fried.
It is, but it's simple. We're doing the same thing again and again. It's the same z value, right? And we're going to convert the 11 and the 14. That's it. 11 minus 10 over 2, boom, 0.5. 14 minus 10 over 2, boom, 2.00.
Letters.
And they give you, I know they give you the, basically you start to plug it in. They
That's
give you
it.
the X and the mean.
That's it. You just plug it in. That's all it is, right? So now, instead of me saying I want to find from 11 to 14, I can simply say that I want to find from 0.5 to 2, right? So we're back to what we just did, all right? So here's an even more simplified graph, all right? The first graph, I would say like, that's there for your understanding, but if you show me this graph, the Z graph, this is all you need right here, right? So 0.5 is right here, 2.0 is right there, right? This is my 0.5, this is my 2, and then you just shade in between. And that's it. That's showing it. And then boom, calculator, answer, done.
It goes right there.
Or for you guys, table. Go ahead.
What did you do there? Just find Z?
That's it. Just find the Z values, right? I converted the X values to Z values. And then if you're using the table, right, here goes your work right here. So to find the probability of 11 less than or equal to X less than or equal to 14, we convert it over to Z values. So we have the probability of 0.5 less than or equal to Z less than or equal to 2.0, right? You can look that up in the chart, right? Or do it in the calculator, your choice. In the chart, the area less than 2.00 is 0.9772. And then in the chart, again, the area less than equal to 0.5 is gonna be 0.6915, right? Subtract them. In the calculator, you get 0.2857. That's it. All right. If you were using,
Right?
uh-huh.
So it says suppose the median family income is normally distributed with the mean of 3,800 and the standard deviation is 3,200. So that's the formula you just showed right now.
Same formula, same thing.
Basically.
Yeah,
Okay.
just plug it in, switch it up, look it up, that's it. Mhm.
What is the probability that the family children are running on X life between 2,800
Mhm.
and 3,200?
Same exact question. The numbers might change, but it's the same question again and again and again. All right, so let's interpret this number a little bit, right? So the probability is 0.2857 that an X value selected at random from a normal distribution with mean 10 and standard deviation 2 will lie between 11 and 14, right? That's what that number means that we're finding. Let's do another example. All right, so the lifespan of a rechargeable battery is the time before the battery must be replaced because it no longer holds a charge. One tablet computer model has a battery with a lifespan that is normally distributed with a mean of 2.3 years and a standard deviation of 0.4 years, right? So what is the probability that the battery will have to be replaced during the guaranteed period of 2 years, right? So let X represent the battery lifespan. The statement that the battery needs to be replaced during the 2-year guarantee period means the lifespan is less than 2 years or X less than or equal to 2. Convert this statement over here. So we have Z is equal to X minus mu over sigma, same thing, plug in the numbers, right? 2 minus 2.3 divided by 0.4, that's gonna give us a negative 0.75. So what does that mean, right? So X less than or equal to 2 means that it's Z less than or equal to negative 0.75. All right. Boom. All right. Indicate the area to be found in figure 7, whatever. Does this area correspond to the probability that Z is less than or equal to negative 0.75? Right. So yes, the shaded area does correspond to the probability that Z is less than 0.75. Let's look at that graph real quick. And pull that up. Yeah. Okay, so we have our normal distribution here, right? Ours with the Z, right? Our standard normal. We know that negative 0.75 is going to be somewhere around here, right? As it is over here. And that just shade that area to the left. And that's it. After that, look it up in the chart. So negative 0.75, boom, you get the answer, and that's it.
Can you scroll up a little?
Mm-hmm. Like here?
No, like with the formula is.
Yeah, right here, right?
Oh, right there.
Yeah, that's the formula at the top right here. And you just plug in the numbers and that's it. Good?
Yeah.
All right. Let's interpret this a little bit. So what is the probability that the battery will fail before the end of the guaranteed period, right? Hint, the probability that X is less than or equal to 2, right, is equal to the probability of Z less than or equal to negative 0.75, right? So we just look it up and boom, that's the answer. We got on the chart 0.2266, which we can round off to say that it'll be about 23%. So this means that the company will repair or replace about 23% of the batteries that they send out. That's what that means. All right. This next topic, you have like one question on it for your homework. Just one. But it's something good to know. All right. So we're going to talk about inverse normal distribution. All right. So sometimes we need to find Z or X values that correspond to a given area under the normal curve. This situation arises when we want to simplify a guarantee period such that a given percentage of the total products produced by a company last at least as long as the duration of the guarantee period. In such cases, we use the standard normal distribution table in reverse, right? When we look up an area and find the corresponding Z value, we are using the inverse normal probability distribution. All right. This too can be done in the calculator, but we got to build up to it. All right. Got to build up to it. So let's look at an example real quick, right? So we want to find X given the probability. So Magic Video Games Inc. sells an expensive video game package. Because the package is so expensive, the company wants to advertise an impressive guarantee for the life expectancy of its computer control system. The guarantee policy will refund the full purchase price if the control system fails during the guaranteed period. The research department has done some tests that show that the mean life for the computer is 30 months with a standard deviation of about 4 months. The computer life is normally distributed. How long can the guaranteed period be if management does not want to refund the purchase price on more than 7% of the Magic Video packages? All right. This is going to be good. This is going to be good. All right. So let us look at the distribution of lifetimes, right, for the computer control system, right, and shade the portion of the distribution in which the computer lasts forever, for fewer months than the guarantee period. If a computer system lasts fewer months than the guarantee period, the full price refund will have to be made. The lifetime requiring a refund are in the shaded area, right, in the figure. This region represents 7% of the total area under the curve. And we can use the table, right, to find the Z value such that 7% of the total area under the standard normal curve lies to the left of the Z value. Then we convert the Z value to its corresponding X value to find the guaranteed period, right? So we want to find the Z value with 7% of the area under the standard normal curve to the left of Z. Since we are given the area in a left tail, we can use table 3 in the appendix to find the Z. So the area value is 0.0700. However, this area is not in our table, so we use the closest area, which is 0.0674, and the corresponding Z value will be negative 1.48. So let's take a look at how we did that. Let's take a look. So graphically speaking, real quick, this is what I'm looking for, right? I know what my mean is, right? The computer will last 30 months, right? Make that a little bit bigger. The computer, I know for sure, is gonna last 30 months, right? But I wanna know at what point, what month will only 7% of them fail, right? That's what I'm looking for. What month will 7% of them fail? That's my guarantee period, all right? So in the table, I want to look that up and find it. So here's how I look that up real quick. Whoops. So you're going to look in the table. We know it's going to be in a negative Z. And we're looking for 0,700, right? We're looking for 0,700. When we look in the table on row negative 1.4, and we come to where the 8 is, right? In between the 7 and the 8, I find a number that's smaller than 0,700. I mean, larger than 0,700, and I find a number that's smaller than 0,700, right? It's in between the two, those two numbers, right? 0.47 and excuse me, negative 1.47 and negative 1.48, in between there. So what do I do with those? Add them up, divide by 2, and we get our Z value. Now to translate the value back to the X value, the real answer to the question, right? Because I'm looking for the X value. At what point should I offer this guarantee? We use the raw score formula, right? So raw score, again, that's on your formula sheet, so you don't got to write it down if you don't want to, right? It's going to be X is equal to Z times sigma plus mu, right? We found our Z value to be negative 1.48. Our standard deviation was 4, that was given to us, and our mean is 30. Plug it in, boom, 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 in about 24.08 months. That's our guaranteed period to guarantee the computers. All right. Only one question in the homework is like that. But I want y'all to understand. So let's interpret it real quick. So the company can guarantee the Magic video game package for 24 months. For this guarantee period, they expect to refund the purchase price of no more than 7% of the video game packages. All right. So it's guaranteed to be good for at least 24 months. All right, so example 6 had us find a Z value corresponding to a given area to the left of Z. What if the specified area to the right of Z or between or is between negative Z and Z, right? How do we do that? Let's take a look. Almost done, almost done. Gotcha. So when we use a table, right, of the appendix, right, to find a Z value corresponds to the given area, we usually use the nearest area value rather than the interpolating between the values. However, when the area value given is exactly half between the two area values of the table, we use the Z value halfway between the Z values of the corresponding table areas, right? So another example demonstrates this procedure. However, this interpolation, right, convention is not always used, especially if the area is changing slowly as it does in the tail ends of the distribution. So when the Z value corresponding to the area is smaller than -2, the standard convention is to use the Z value corresponding to the smaller area. Likewise, when the Z value is larger than 2, the standard convention is to use the larger area, right? So real quick, let me show y'all what that means. All right. So inverse normal. So using the table 3, right? And we find this area, this is the left tail case, right? So when they're asking for less than, right? What we're gonna do is we're just gonna copy the Z. So for the left tail case, you just look up the number and then you're good to go, right? For the right tail case, here we go. This is where it's gonna get a little tricky. So right tail case, so given that you have an area A and it's to the right of Z, right? You're going to look it up in a table and do 1 minus that area, right? Before to get what that Z value is gonna be. Right? So we know that whenever it's greater than. And if it's in the middle, we're gonna have 2 Z's, right? some questions might ask you in between which two numbers, you know. So for the center case, the given area A is symmetric and centered above z equals 0, right? Half the area lies to the left and half to the right of z equals 0. For the center case, look up the number 1 minus the area, right, in the body table, and then use the corresponding to find the positive and the negative z value. That's it.
Because we don't want, little explanation, right?
Mm-hmm. Oh, like, no, just a number. Yeah, no, just a number. Right. Let me do an example real quick. Let's say I want to find a z, right? So find a z value such that 90% of the area under the standard normal curve lies between negative z and positive z, right? So this is an example where they're giving you a probability and you're going to give me back the z value, all right? Let's take a look at this. So the area between the negative z and the positive z, right, is 90%. So that means in between these two z values, z and negative z, right, this is 90%. Right? And I want the z values corresponding to that. So to find the corresponding z values, we do 1 minus the 90% and then divide by 2, right? So remember, 1 is doing the whole distribution, everything, and you subtracting out the middle part. That's the 90%, right? So what's that leaving you with? That's giving you the 2 tail ends. But what you have to do is divide it by 2 to get just the left tail end. Right? In this formula, yeah. This is when it's centered, when it's in between two numbers, right? When you divide by 2, you have this area here. This area can help you to find the negative z value. The positive z value is going to be the same number, but positive. And that's it. All right? When you look at the homework, you'll see how simple it is. Like, it wouldn't surprise me if y'all finish the homework like before you leave today. You know?
Yeah, we always say that.
Yeah. That too, right? So looking in table, whatever, right? We see that 0.05 lies exactly between the areas of 0.0495 and 0.0505. The halfway value between z equals negative 1.65 and z equals negative 1.64 is z equals negative 1.645. Therefore, we conclude that 90% of the area under the standard normal curve lies between the z values of negative 1.645 and 1.645. All right, so that's the z values right there. Just to show you the table where we found those. If you look at the negative table, go down to where row negative 1.6 is, right? You'll see in the row right underneath the 4, the 0.4, you have two numbers that one is bigger, one is smaller, right? And we look at how far they are from the number that we're looking for. If it's exactly in the middle, you add the two z values together and divide by 2. That's it. Right? So negative 1.64 plus negative 1.65 together and then divided by 2. And that's how we get the negative 1.645. Right? All right. Now, let's say you want to do this in a calculator, right? You want to go through all that hustle and bustle, right? Let's take a look at an example real quick and we'll talk about how to do it in a calculator. Because your final doesn't have multiple choice. That's right. I mean, but it's so simple. Like, look at the homework. Look how easy the homework is. Let me see. All right, let's look at this. So find the z value such that 3% of the area on the standard normal curve lies to the right of the Z, right? So step one, we got to draw and sketch the normal distribution curve. Boom. There you go. 3% is this blue shaded spot here. That's 3%. And the rest of it to the left-hand side is 97%. Right? Basic. We know that. Right? I'm looking for this one Z value right here. Right? Now, I can't do anything with that 3% using the table that I have, right? I'd have to look up the 0.97 and boom, that's how I'd get through this question. But on your calculator, we can look this up. All right. So let's take a look at the answer real quick if you were to look it up in the table, and then we'll talk about the calculator. So the first thing we do, we have to find the area to the left of Z, which is basically just 1 minus the 0.03, which will give us 0.97, all right? And then in the table, the closest area to 0.97 is 0.699, right? So they're gonna use Z is equal to 1.88, right? So we're gonna remember that number, right? 1 second, let me just get my calculator real quick. If we wanted to find that in our calculator, here's how we would do that. 1 sec, gotta make this a little bit smaller. All right, gonna need a little bit of help from you guys, but I'm gonna walk you guys through it. So the first thing that you wanna do, if you want us to do this in a calculator, right? We're gonna press second, right? Second is the blue button on your calculator, right? You're gonna then go to distribution. That's the data button on the calculator. After that, I want you to go to the right to where it says DISTR. And then you're gonna go down. After you go to the right, you're gonna press down. And I want you to go down to where it says, wait, I can't, that's not a good R. Normal inverse, INV. Is INV normal? Whoops. See, I told y'all, they kicked me out of the spelling bee in 5th grade. I don't know. INV normal, right? All right, and when you click it, what comes up? It says area, right? So our area, right, that we were given, or that we found, excuse me, is what? 0.970, 0.9700. So you can just put for area 0.97, or if you feel like putting the extra zeros, go ahead. Right? And what's next after that? The mean, right? This is a standard normal score. So what's the mean? 0. What's the standard deviation?
1.
Good. Oh, +1, +1. All right, then you hit enter. Perfect, and that's what our answer is. Same answer right off the chart. So that's how you do it in the calculator. But she needs it, he needs it. All right, so let's take this up a notch, right? I'm gonna take this up a notch. Still using the calculator though. Suppose the time to complete a test is normally distributed with the mean mu is equal to 40 and a standard deviation sigma is equal to 5 minutes, right? How many minutes can we expect all, can we expect all but 3% of the test to be completed, right? So we're looking for an X value such that 3% of the normal distribution lies to the right of X, right? So in part C, we found that 3% of the standard normal distribution curve lies to the right of Z equals 1.88, right? All we have to do is we have to convert that into the X value using the raw score, right? So our raw score formula, which is on your formula sheet, is X equals Z times sigma plus mu. Just plug in the numbers that we found, right? We found 1.88, boom. Times the standard deviation, which is 5, boom. Add that to 40, boom. So it's gonna take us 49.4 minutes, right? So all but about 3% of the test will be completed after 50 minutes. That's it. Just type it in and you'll get the answer right there. Simple, simple, simple stuff. All right. All right. So you can use a table to do it as well. All right. So what this is saying is that, let's say that you didn't want to do or find the 0.97, right? You could have found the negative Z value corresponding to it, right? By looking up the by looking up the 0.03, right, in the table. And then we would have found negative 1.88 on the corresponding table. And then just change that to positive and do all the work again. That's what it's basically saying. All right. Not my favorite method, but it is an option. All right. So that's it. You guys can start your homework. I have a little bit more to talk about that's not on your homework, but it's something for the 4-year school. All right. And I thought this was really, really interesting. So I thought you guys might want to hear it. All right. All right. It's gonna be quick. It's gonna be quick. It's gonna be quick. But you guys can start your homework right now. So the next thing I want to talk about is called checking for normality, right? So how can we tell if the data follows a normal distribution, right? So there are several checks we can make, right? And the following procedure list are some guidelines. This is really, really cool, all right? So this is a way to tell if the data that I have is normal and I can do everything that we just spoke about today, all right? Not asking you guys in this in like your homework or on a test, but I thought it was really interesting, right? So procedure, right? So how to determine whether the data have a normal value. So the following guidelines represent some useful devices for determining whether or not the data follows a normal distribution. You can use a histogram, right? So make a histogram for a normal distribution. The histogram should be roughly about the bell shape, right? Bell-shaped curve, right? You can look for outliers, right? So for a normal distribution, there should not be more than one outlier, right? One way to check for outliers is to use the box whisker plot. So recall that outliers are those data values that are above the third quartile, greater than 1.5 times the interquartile range, or below the first quartile by an amount that's greater than 1.5 times the interquartile range. All right. Really interesting. But this right here is probably the most interesting part or way to tell if a graph is normal or not. I mean, excuse me, if the data is normal or not, right? So normal distributions are symmetric. One measure of skewness for sample data is given by the Pearson's index, right? So Pearson's index is equal to 3 times the sample mean minus the median divided by the standard deviation. So an index value greater than 1, right, or less than -1 indicates skewness, right? So skewed distributions are not normal, period. All right. Again, I thought that was really cool. That's it for today. All right, so have a great day, everyone. Appreciate that. Thank you, thank you, thank you. Yes. You're welcome. All right. Any questions? Or I can end this now. Okay, Shannon? And all right, so we're just gonna do homework. So everybody, have a good weekend if you're watching the review, and we'll catch up next time. I got you. Hey, just leave right there.